measure theoretic, in a way, solution. And then we want to commute this into to a solution which is pointwise defined everywhere, so to a continuous solution. And now we go into the world of the Giorgi density conditions. Okay, the Giorgi density conditions are conditions on the density of level sets that are transformed into everywhere conditions. So now you really see at a microscopic level the transition between a measure theoretic approach, a measure theoretic information, to an everywhere information. So density of level sets, it's commuted into an everywhere information. On level sets. So, and this goes via two lemmas, and let me present you the first of the two lemmas. So the proof of Hilbert continuity splits into two lemmas, and you see this approach, I mean, if you go to textbooks, very few textbooks present this, this approach, but if you look, for instance, at Di Benedetto's textbook, it's a general textbook, then you can find this approach, which is really the real approach, because then this opens the way to a real philosophical approach. That is, you want to commute and prove pointwise inequalities using density informations. Density informations, and actually it is a because actually you very often see these kinds of things in proof via pointwise and integral estimates. Now we go to real density conditions. So the first lemma of the Giorgi, is the following one. Okay, from now on, let me take a ball. All the balls will be concentric, okay? So, for instance, a ball centered at 0 after translation has no point. We take, we define the oscillation over a ball of radius 2 rho as the sup over b 2 rho of u minus the inf over b 2 rho of your function. And now you see you're using the function that u is bounded. Why? Because now you can define these quantities are well defined. Okay. Okay. In particular, let me call it omega. And in particular, let me call you mu, this quantity, and mu minus this quantity. Okay. And then I want to go to what happens in B rho. And the first lemma is the following one, lemma 1. Okay, the lemma 1 tells you that for every epsilon between 0 and 1, the following thing happens uniformly. It happens uniformly the following. For every sigma between 0 and 1, there exists a mu depending on sigma and the data, that is L over mu and n, in 0, 1, such that if the density of this set in the ball B rho is small, so if the density of the level set where u approaches its maximum, you see, this is the oscillation. Okay? Take, for instance, assume that u is positive and the oscillation is equal to 1. Okay? This is B rho. This is the maximum. if the measure of the level sets u minus epsilon in this condition is small, okay, so you're measuring the ratio, the portion where u exceeds this quantity, then it happens